Hello. So in this video, we're going to learn a method, an iterative method for approximating the solution to first order differential equations. Now, as I've mentioned in previous lectures, differential equations can be very difficult to solve. Sometimes you just can't solve them. But still, because they represent all kinds of physical phenomena and applications, we need to be able to somehow at least approximate the solutions. So recall that a differential equation is an equation that contains derivatives of a function y, the variable y, not variable, the function y, and the variable x. So given a differential equation, the goal is to find the function whose derivative, if you plug into the equation, will satisfy the equation. So how can we approximate this, right? It's a function that we're trying to find. So suppose that, well, let's first, I guess I need to state the problem at hand, like formalize it. So the problem, approximate the solution to a differential equation of the form y prime equals to some function f of x in y. I don't know why there's knots there. It should be just x and y. Yeah. So y prime is a function of x and y, which passes through the point x naught, y naught. Okay, so this is the problem at hand. And what is the information that we know, right? So we are given this and this. So we have a point that the function passes through, and we have the slope, right? So maybe I should write that here. So find the function f that is equal to y. That's our goal, okay? Okay, so, and we're given this information. So we know this function passes through this point, and we also know the slope of that function at a given point. That's the important part. This tells us the slope, because the derivative at that x and y, if we have an x and y we plug in, we'll have the slope of the function at that point. So imagine that we have so we have like our Cartesian plane here. And then let's go ahead and put in a function. So this will be the exact solution to the differential equation at hand. And we don't know what that function is. That's why I dashed it like that. So this is the exact solution. Okay. So yeah, so exact solution for this differential equation. Okay. Now we do not know this. Okay, that's why it's dashed again. Just emphasizing that one more time. We do not know what that function is. But we know that the function passes through this point x naught, y naught. We're assuming that we're given that in the problem statement. Right? So for example, we know make sure you can read that. We know that the function does pass through this point. Okay, so how can we use this to help us find an approximate solution? Well, not only do we know that point, but we also know the slope of this function at that point. We know the slope of that line. How do we know the slope of that line? Well, what is that? That is precisely that. If we plug in that point into the derivative, which that's the derivative of what we're seeking, right? Right, so like f prime of a point is equal to y prime, right? So we know the derivative, we know the slope of that tangent line there. So we can use this as like in a little like interval around x naught, we know that this line kind of behaves like this function because the slope of this line is equal to the slope of the function at that point. So in a small little interval around x naught, this line kind of behaves like the solution. Now, with that observation, then what we can do is say, this line behaves like that solution. So let's say, let's pick a new x1, which is equal to x naught plus h, where h is just some positive number. So we've moved over distance h. And we get a new y. Well, what is that y going to be equal to? Well, again, like just like we did with Newton's method, recall that y1 minus y naught is equal to m times x1 minus x naught, right? That's the equation of a line. And what do we know in this equation? We know that, so this is that line right there, right? We know that. We know that. That's just f at x naught, y naught. X1 is, we just went to the, oh, this is just the difference in x. That's just h, right? How far are we? X1 minus x naught is just h. And that is f at x naught, y naught. That's the slope of that tangent line, right? Because that's what the formula gives us. So altogether, if we solve, we get that y1 is equal to y naught plus h times f x naught, y naught. So that's what gives us our y1 here. But then, right, then we know that, so here we use this line to match the slope of the tangent line there. So then here, we know the slope of the tangent line at that point, right? The slope of the tangent line there, y prime is equal to f at x1 comma y1. At each point, for each value of x and y, we know the derivative or the slope of the tangent line. So if the actual solution has tangent line like that, then if we're trying to approximate that, we should kind of mirror what's happening there. So then we're going to mirror that tangent line. And then here, this is going to be x2 equal to x1 plus h. And then this will be y2. And y2, as you can probably guess, we form in a similar manner. We say y2 is equal to y1 plus h times f at x1, y1. And then, again, we know the slope of the tangent line at x2, y2. It's like that, because at each time we can evaluate this function to get the slope. So it's a little bit steeper now, or like that. And we keep on going, and look at what's happening with the yellow lines here. This here is an approximate solution to this problem. So what are we doing, right? We're using the information about the function the solution passing through this point here. And then we're also using that we know the slope of the tangent line to iteratively build an approximate solution to that function. Iteratively build a function that approximates the solution to that differential equation. That's what I meant to say. And you can imagine if we use smaller and smaller step sizes, so h is like your step size. So if instead of using that size h, we did like there, and if we did that size h, then you can see that that green line there is a closer approximation to the true solution, the exact solution, by choosing smaller h. Okay? So the idea is to say x n is equal to your previous xn, or your previous x, plus h, and yn is equal to your previous y, plus your slope, plus your h times your slope. H is your difference in x at each step. So this would be at x of n minus 1, y of n minus 1. This here, these two things here, this is called Euler's method. It's an iterative method. By iterative, I mean we have initial x naught, y naught, we have initial x and y, and we iterate using the previous terms to build a sequence of x's and y's. And in this case, that sequence of x and y's, the y's are approximating the exact solution to the differential equation at hand. Okay? So maybe we should look at an example. Okay. Where's my erasing? So we want approximate. So approximate the solution to, say, y prime is equal to 2x plus y that passes through the point 1, 1. Okay, so first let's do this by hand, and then I'll show you how to quickly program it using Python. There's the method. This is our problem here. So let's look at the solution here. I'm going to try to plot it the best I can. So, God, this is going to be really hard to do with appropriate scaling, I'm assuming. Alrighty, the scaling is going to be thrown off. Okay, so y prime is, so our capital F is equal to this. So this gives us the slope at a given point, x comma y. And then we know our initial point is 1, 1. So we know, I'll use yellow instead. We know we pass through this point right here. Okay. So what's the slope of the tangent line at that point? For the solution that we're seeking, like right now, we have no idea what the solution looks like. So, all right, so f of 1, 1. So what is that? 3. So the slope is 3. Let's pick h to be equal to 0.5 or something. Okay. So then x1 is going to be equal to 1.5. So 1 plus 0.5. So there's our x1 right there. And then y1 is equal to, I'll just write it out, y naught plus h times f at x naught, y naught. So this would be 1 plus 0.5 times 3. Okay, so we have 1 plus 1, so it's like 2.5. So we're like right there. So this is like x1, y1. Okay. So let's just iterate this maybe 1 or 2 more times. All right, so then f of 1.5 comma 2.5 is going to give us the slope of the tangent line at that point of the exact solution. So what is that? So 2, so the 3. So 3 plus 2.5, so 5.5. Okay, that's the slope. And then our new, so our x2 is going to be equal to 2. So we're here now. And then our y2 is equal to 2.5 plus 0.5 times our slope. So what is it, like 2.75 there? So 4.75. 5. It's a little bit over 5, so it's like somewhere up here. So at 2, it's like somewhere like right there, maybe. And if we kept on doing this, we would get an approximate solution to this this differential equation that passes through there. Okay, you can think of this almost like as like a an initial condition, maybe. Which, by the way, if that's your differential equation, when x and y are 0, the slope is 0. So I imagine that, so the slope is 0 there. I imagine that the exact solution probably looks like some type of exponential like that or something. Okay. So now I'm going to pause the video and then I'm going to pull up the Jupyter notebook just to show you how to solve this using Python. Okay, so let's go ahead and look at how to program this using Python. Okay, so I went ahead and opened up Anaconda, then I opened up a Jupyter notebook, and then I made a new Python 3 file, and then here it is. Okay, So the way that this is going to work is that, so we're going to plot and we're going to, do we even need NumPy? No, we don't even need this. We just need plots to look at the solution that we make. So import matplotlib.pyplot as plt. And then here we define our derivative. So y prime is equal to this function f of xy. And in our specific case that we just looked at, it was 2x plus y. So I make a function to do that. We used step sizes for h of 0.5. I'm going to use a smaller one. So 0.15 is our step size. And if you recall, I'll use capital X and capital Y to denote our X and Y values. As I mentioned a few moments ago, Euler's method builds collections of X and Y. So let me fix this right here. Capital X, capital Y, capital X, capital Y. So I initialize X to be the list with 1 and Y to be the list with 1. So this is because X0, comma Y0, like this point that we pass through, this is equal to 1, comma 1. So X0 is 1, Y0 is 1. And then I'm just going to iterate this 15 times. So I set a counter and I say, while the counter is less than 15, look at how I update my, oh, this should be capital X here. So my X new that I make is my previous X, which is -1 goes to the very back of the list. So this will be our previous X plus our step size H, okay? And then our Y new is going to be our previous Y plus H times our function, our derivative, evaluated at our previous X and our previous Y, okay? So -1 index always goes to the back of the list. So we start off with 1 and 1. So when I make X new here, X -1 is going to be 1. And then I'm going to add H to that, and that'll be my new X. And then my new Y will be our previous Y, which is given by the -1, plus step size times the derivative at our previous X and our previous Y. And then I put those values into X and Y. And the append method here will put these X new and Y new into the back of capital X and back and capital Y. So when we come back around and we go to -1, we're always going to look at the most recent things that have been added to our list. And then, of course, we do our count plus equals 1. So that after we do this 15 times, we break out of this while loop. And then we just plot X and Y. Yeah, so that should be it. There. And maybe if you want to see like the points that we're actually making, you can use the scatter method. Let me see if I can change the color. So there, the plot method here is just connecting all the points that we produced. And then scatter is just doing a scatter plot of the points. So if I made this H here bigger, if I made it like 0.5, you can see how, so maybe if I make it 0.5 and we do like 25 iterations, or maybe 0.75, we see that this here is approximating our solution, okay? Maybe if I do 5, what happens then? Right. Now, again, as I was mentioning, when the step size is large with respect to the number of times you iterate it, you have this kind of like, this definitely doesn't look like a smooth function. Like there's these corner points here. But if you make H really small, it starts to becomes smooth looking, and it's behaving more and more like the actual function. Right? If I do that 100 times with these super small steps, let me just get rid of the scatter. You can see like it's starting to look like it's, and this is an approximation to the actual solution to this differential equation. Okay. Okay, so that will be it for this recording. Thank you for watching.